In this section, we'll use no-load and lock rotor tests, as well as a DC measurement of the stator winding resistance to determine the parameters for a forward and backward field circuit of an equivalent circuit model of a single-phase induction motor. The induction motor is a 1 horsepower, 2-pole, 240-volt motor operating at 60 Hertz. The DC measurement of the stator winding resistance, RS, is equal to 1.6 ohms. The no-load test results are, with an applied no-load voltage, VNL, of 240 volts, which supplies a no-load current of INL is equal to 3.8 amps, and draws a no-load power of PNL of 190 watts. The locked rotor test results are when applying a locked rotor voltage of VLR is equal to 88 volts, plus a locked rotor current of ILR equal to 9.5 amps, and drawing a locked rotor power PLR is equal to 418 watts. Our task in this problem is to establish the motor equivalent circuit parameters. The no-load test gives us the total magnetizing reactance, 𝐃𝐈. We divide it by 2 to account for the forward and backward rotating fields in the double revolving field circuit model. Each branch gets half of the magnetizing reactance. At no load, the rotor draws negligible current, and therefore the rotor branch appears as an open circuit. Therefore, IS is equal to I₄. The equivalent seen at the terminals is purely reactive and only sees the magnetizing reactance. ZNL then is equal to JXphi. Therefore, the magnitude of Xphi is equal to the no-load voltage over the no-load current, and we know these both, so we can substitute the actual values, which is 240 divided by 3.8, resulting in 63.2 ohms. The no-load test gives us the total magnetizing reactance, Xphi. We divide it by 2 to account for the forward and backward rotating fields in the double revolving field model. Each branch then gets half of the magnetizing reactance. In the locked rotor test, we apply 88 volts as Vs, and we will use it at 0 degrees as our reference phasor, and measure the current, which in this case is 9.5 amps, and the power, which is 418 watts. With the rotor locked, the slip S will equal 1, making the rotor resistance for both the forward and backward rotating field circuits equal to R'(S) divided by 2. Furthermore, the magnetizing current will be almost negligible compared to the current flowing in the rotor circuits. This means that we can redraw and relabel our equivalent circuit to look like this. Since the real power equals VI cos phi, we easily can calculate the power factor because in the locked rotor test we have measured the power, voltage, and current to give us the power factor cos phi, which is equal to the power all over the voltage times the current. Plugging in our real values, we get 418 divided by 88 times 9.5, which equals 0.5, the inverse of which gives us the power factor angle of 60 degrees. Because the current lags the voltage in an induction motor, the angle of the ILR, the current phasor, is minus 60 degrees. Therefore, the current phasor or vector ILR is 9.5 at minus 60 degree amps in polar coordinate formation, or 4.75 minus J 8.227 amps in rectangular coordinates. We are now going to use this information along with the information from our locked rotor test to determine the rest of the parameters. We can do that by analyzing this as a simple series circuit. However, our first step is to find the stator current IS. It is what is left of the locked rotor current ILR once we subtract the magnetizing current I-phi. This fact is described by the equation IS is equal to ILR minus I-phi. We can calculate the magnetizing current using Ohm's law, which is the locked rotor voltage divided by the magnetizing impedance J(X)phi. And we know these terms. VLR, or the locked rotor voltage, is 88 volts, and we just finished calculating the reactive impedance, which is 63.2. That calculation gives us 1.392 at 90 degree amps in polar coordinates and 0 minus J 1392 amps in rectangular coordinates. We can move that current calculation over to the left and subtract it from the locked rotor current. This result of which gives us the stator current IS of 4.75 minus J 6.835 amps. Once we know the stator current, we can forget about the magnetizing current and just treat the rest of the circuit like the analysis of a series circuit with a current of IS. As a reminder, I want to keep track of the fact that we have already measured the stator winding resistance RS of 1.6 ohms. And let's move it up here for future reference. Looking at our series circuit, we have 4 resistance values, which would added together give us RS plus R primed S, the sum of which can be found by the power dissipated in the locked rotor test divided by the stator current magnitude squared. Plugging in our actual values, we get 418 divided by 8.32 squared, which equals 6.03 ohms. Rearranging our equation, we get R primed S is equal to 6.03 minus RS, which equals 6.03 minus 1.6, and that comes out to 4.43 ohms. Now we still have one more parameter to calculate, and that is the leakage reactance XL. We start by calculating the total impedance of our series circuit, ZR, which is equal to the locked rotor voltage all over the stator current IS. We have already calculated these values and can substitute them, so we have 88 divided by 8.32 to give us 10.63 at plus 55 degree ohms. In order to find the leakage reactance, all we have to do now is to find the trigonometric sine of ZR, which is the sine of 55 degrees times 10.63, and that equals 8.71 ohms. We have now successfully completed the calculations for all of the parameters of our equivalent circuit. Returning to our single-phase induction motor equivalent circuit, where all of the parameters have been calculated and the slip remains a variable, we can see where the parameters now fit into the equivalent circuit diagram. Notice that all of the parameters are divided by 2, where each forward and backward rotating field circuits now have 1/2 each of the calculated parameters. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my stand store for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB.